So if you've been following this series of lessons in order, we've covered all of the gas laws, at least the basic versions of them, and now this lesson is all about just doing some practice. So for this problem, we've got a mass of carbon dioxide of 2.34 grams. We want to find the volume of carbon dioxide at STP. STP is standard temperature and pressure. So standard temperature is standard temperature is 0.00 degrees C, but we can't do any math with gas laws when we're in degrees C. We have to convert to Kelvin. You should know that the Kelvin standard temperature is 273.15. Okay, Kelvin. Standard pressure is 1 atmosphere. So we've got, we're trying to find volume. We've got temperature and pressure. We don't have everything we need to find the volume yet. What you have to realize is, as you learned from the last unit, if you have grams and you know the chemical species, you can find moles. It's just using molar mass to convert. So the molar mass of CO2 is calculated in this fashion. Carbon's atomic mass is 12.01. You can look that up on your periodic table, and oxygen is 16. We have 1 carbon in CO2, so that's 12.01. We have 2 oxygens in carbon dioxide. That's 32. So that's 44.01 grams of CO2 in 1 mole of CO2. So if we have grams of CO2 here, 2.34 grams of CO2, you put that over 1. You can convert to moles using this equality statement. Grams are going to go on the bottom, 44.01 grams of CO2, 1 mole of CO2 on the top. Cancel units, cancel species, just like x's and y's in algebra. The math is 0.0531 697.34151 moles of CO2. Round that off to 3 significant digits because this is the measured or calculated number with the least number of significant digits. Leading zeros like this are not significant. 1, 2, 3. And round it off to 0.053. This 6 makes the 1 round up to a 2 moles of CO2. So now we do have moles. So now N, which is the symbol we use for moles, is 0.0532 moles. All right, we're getting really close here. We've got V, T, P, and N. So that'll fit the ideal gas law. PV equals nRT. We just have to figure out which R to use. The R we want to use will match the pressure unit. So we look up R on the references, and we can see that the value of R that has atmospheres in it is this one, 0.0821. So R is going to be 0.0821 liters times atmosphere. Liters times atmosphere. And when I have moles -1 exponent, that means moles is on the bottom. When I have Kelvin -1 exponent, it means Kelvin's on the bottom. And that's the version of R we're going to use. And we're trying to find the volume, and you can plug in all the values you have and then rearrange everything to get the volume. Or we can rearrange the equation now for volume. So if I have this equation, I can set up so volume is equal to N times R times T times 1 over P. Now if you don't know how to do this, and get it right when you do the math, see me and I'll help you with that. But this is just simple algebraic rearrangement. So we're going to say volume then is equal to the moles, which is 0.0532. I put that over 1 to keep everything kind of arranged neatly. R is, we said, 0.0821 liters times atmospheres over Kelvin times moles. Let's see, the next thing is T, which we said was 273.15. That's it right there. And then 1 over the pressure. And the pressure we said is 1 atmosphere. That's one we're using anyway. We can cancel out a bunch of stuff. Moles cancel because anything on the top and bottom like that get canceled. Atmospheres cancel. Kelvin cancels. We're left with volume, or liters rather, which measures volume. We know we probably set it up right. Then we do the math. And we get 1.193042718 liters. We're going to round that off to 3 significant digits because this number and this number and this number all have 3 significant digits. This is measured, this is a calculated number, this is a measured number. So of the measured and calculated numbers, 3 significant digits is the least. That's what we want in our final answer. Underline everything after the first 3 significant digits. Use an arrow to show we're rounding off. And write the answer of 1.19 liters equals the volume we're seeking here. At what temperature will 0.654 moles of neon gas occupy 12.30 liters at 1.95 atmospheres? So we've got moles. That symbol is N. 0.654 moles. We've got a volume of 12.30 liters. And we've got a pressure of 1.95 atmospheres. Okay? So I have most of what I need for, and I'm trying to find temperature. So I have most of what I need for PV. PV equals nRT. The only thing I need to figure out is which version of R to use. And you choose R based on your pressure unit. So I've got, I'm trying to find, I've got P, I've got V, I've got N, trying to find T, so all I need is to figure out which R to use. The version of R that has atmospheres in it is this one right here. So 0.0821 liters. Now it's shown in here as liters, atmosphere, moles, -1, K exponent -1. And what that means is that moles and Kelvin, moles and K, go on the bottom of a fraction. So now all we've got to do is plug in. We're trying to find T. I always like to isolate the unknown first when we get to something like the ideal gas law. All right? That's up to you, but it works out better for me to do that. So if I have PV equals nRT and I want to get T by itself, I'm going to divide by N and R. And that's going to allow me to cancel out N on this side and R on this side. And so the equation I'm actually going to use is T equals PV over NR, or PV over 1 times 1 over N and 1 over R. Okay? Either one of those works. That's fine to do it either way. Okay? So temperature then is equal to pressure, and pressure is 1.95 atmospheres over 1. V, 12.30 liters. Okay. I'm going to put N on the bottom, moles on the bottom, and we have 0.654 moles, 1 over 0.654 moles. Okay. Now, to put R on the bottom, okay, basically you just have to flip the thing. So moles goes on top, liters and atmospheres goes on the bottom with the number. Hold on to your hats, folks. If I need to put R on the bottom, R is this particular R is 0.821 liters times atmospheres over Kelvin times moles. Alright? I'm going to put that on the bottom of a fraction. Okay? So I'm going to put 1 over 1, because 1 over 1 is 1, right? That makes sense? Okay, I've got a complex fraction now. That makes sense? You have a complex fraction. The process you use to solve or find a solution for that fraction is to write 1 over 1 and then invert this and multiply. Which that times that, 1 times this and 1 times this just gives you Kelvin times moles over 0.0821 liters times atmospheres. Okay? So, up here, if I'm going to have 1 over R, if you can kind of think ahead a little bit, you know you got to flip it, right? Does that make sense? So mathematically, I suppose that's one way to work it out. Might not be the way your math teacher would work it out, but it's the way that I think about it anyway. Kelvin times moles over 0.0821 liters times atmospheres. So 1.95 times 12.30. These two things are just ones. We don't have to worry about that, but we're going to divide, hit enter. And this is the system I've taught you because it works on every calculator. You can do it on some calculators a little bit easier maybe. I don't know. I think this is pretty easy personally. But I know this works on every calculator. So multiply what's across the top, hit enter, then divide by 0.654, enter, then divide by the second number on the bottom, 0.0821, enter, and I get that number. Cancel out everything we can cancel out. Atmospheres cancel, liters cancel, moles cancel. The only thing we have left is Kelvin, and Kelvin is a measure of temperature. I know I've got a pretty good chance that I set it up right. Okay? And so this is Kelvin. We want 3 significant digits because most of these measured or calculated numbers have 3. This has 3 significant digits because leading zeros are not significant. So 1, 2, 3. Underline everything else. Draw the arrow to show they're rounding off. Round the 6 up to a 7 because of this 7 here. And there's the answer we're looking for. If 2 liters of hydrogen, originally at 25.0 degrees C, and 750.0 millimeters of mercury are heated until a volume of 20.0 liters and a pressure of 3.50 atmospheres is reached, what is the new temperature? Alright, so we got 2 liters of hydrogen, 2.00 liters, that's a volume. 25 degrees C, that's a temperature. We can't solve any problems with degrees C, so we need to calculate the Kelvin temperature. Let's see, 25.0 degrees C plus 273.15. 298.15. Got an empty slot above the 5, got to round that off. this is the Kelvin temperature, which is going to be 298.2 Kelvin. So this is better represented as 298.2 Kelvin. We've got a pressure of 750 millimeters of mercury. If you look on the test references, there it shows you down here at 1 atmosphere, which I hope you already know, we've used it enough. That's a pressure unit is equal to 760 millimeters of mercury and 760 torr. So that just tells you right there those are pressure units. Okay, just to help you when you're doing quizzes and tests. Well, it's right. It's kind of right there, kind of a reminder for you on the test references for this class. Okay, that it is pressure. In case you look at that and say, well, that's a length measurement. Well, that's also how we measure pressure. Has to do with where the mercury rises to or drops to on a glass tube device that's measuring the pressure. Okay, and then we got a volume of 20 liters and a pressure of 3.50 atmospheres. Okay, and we want to find a new temperature. All right, we got to sort all this out and figure out which temperature and which pressure we're talking about. So we have 2 liters of hydrogen at an original temperature of this, and this this pressure. So this must be V1, T1, and P1. Okay, and then we're going to heat it. So we're changing the temperature. That's temperature 2, and when we heat it, we get a volume of this. That's a new volume, and a new pressure of this. Okay. So if you look on your test references, you'll actually find the equation you need here. Okay, it's right here. P1 times V1 over T1 equals P2 times V2 over T2, because it matches all of these units. We have all these variables we've listed up here. V1, T1, P1, V2, P2, T2. Okay? So the equation we're going to use is P1 V1 over T1 equals P2 V2 over T2. The only problem we're going to have right now, and you might see it right now and know you have to fix it, or you might start the problem and see you need to fix it. Okay? It's okay. If you're putting it all in here and you start to do the math and you realize you can't cancel your pressure units, then you know you've got to convert your pressure units. Does that make sense? So what I'm going to do is to show you what happens. You may have already solved it by solving your pressure units to start with, which is great if you notice that ahead of time. But even if you don't notice ahead of time that you've got to convert pressure units from either millimeters of mercury to atmospheres, atmospheres to millimeters of mercury, once you get there, if your units don't cancel, it'll show you needed to cancel them. If you use the system I've taught you, which is to always set it up in dimensional analysis. Okay? So let's plug it in and see how that works. So we've got pressure 1 is 750 milliliters of mercury. And volume 1 is 2 liters. And then temperature 1 is 298.2 K. And over on the right-hand side, P2 is 3.50 atmospheres times V2, which is 20 liters. And T2 is what we're trying to find. Okay? So what I want to do is get T2 by itself. Now, whenever you see a unit like this or an unknown on the bottom of a fraction, bells and whistles should be going off in your head. Actually, bells and whistles should have gone off in your head when you saw this 25 degrees C, because you know you're supposed to convert it to Kelvin. But we can't solve directly for an unknown that's on the bottom of a fraction. We've got to flip it. So I'm going to flip everything. So I'm going to have 298.2 K over 750.0 millimeters of mercury times 2 liters. And that equals T2 over 3.50 atmospheres times 20.0 liters. Okay, now we've got the unknown on the top of a fraction. That's fine. So I want to get the unknown by itself. And I need a mathematical operation that will get me there. So this, I'm taking the unknown, I'm dividing by these. To get rid of those on this side, I'm going to multiply by this on the top of a fraction. So 3.50 atmospheres times 20.0 liters over 1. And that's going to allow me to cancel those out, leaving me with T2 by itself. But you can't just do that without also doing the same thing to this side of the equation. What you do to one side of the equation, you must do to the other. Okay? You can think of it as being fair, but mathematically it won't remain equal unless you do that. So 3.50 atmospheres times 20.0 liters over 1. Now I can go through and cancel things. I can see that now I can go through and cancel things, and I can see that 3.50 atmospheres cancels 3.50 atmospheres, like x's and y's in algebra. 20 liters cancels 20 liters, like x's and y's in algebra, leaving T2 by itself, which is what we want to do. Over on this side, I can cancel units of liters, but I'm looking here, and I can't cancel atmospheres with millimeters of mercury. So either I've got to convert this to atmospheres, or I've got to convert this into millimeters of mercury. Either one works just fine. Does that make sense? All right. Does anybody have a preference? No? Okay. Somebody wants me to convert atmospheres to millimeters of mercury. So I'm going to put 3.50 atmospheres over here over 1. And we've been doing this for, I don't know, at least a month and a half now. Where you set up your starting amount over 1, find an equality statement. In this case, there's the equality statement right there. It's already written out on your references, so we're going to write it out so we know we got the right thing here. 1 atmosphere equals 760 millimeters of mercury. Now, you need to be careful about this, because you would look at that and think, well, I've only got one significant digit there. But that's an absolute. Okay? It's not like there's any measurement. You know, we have to round off to the measurement or calculate a number. That's an absolute. So 1 atmosphere is infinitely significant. 760 millimeters of mercury is infinitely significant. So those are absolute numbers. Okay, we're not going to use either one of these two for rounding off. We're going to round off our final answer to 3 digits. So we've got this equality statement to write this conversion unit. I want to put atmospheres on the bottom, 1 atmosphere, and 760 millimeters of mercury on the top. So we're going to take 3.50 and multiply that times 760, and I get 2,660 millimeters of mercury, and I need to round it off to 3 digits. 1, 2, 3. Need to get rid of that digit, and anytime we get rid of a number in the ones place, you've got to use scientific notation. So the implied decimal place here gets moved 1, 2, 3 places to the left. We round it off to 2.66 times 10, 1, 2, 3, 10 cubed millimeters of mercury. Does that make sense? All right, so I need to plug that in there, here for this. I suppose you could just mark it out and put that in there. Okay, is that okay? Y'all want to do it that way? Is that all right with you guys? All right, so I'm going to take this. Since I have the work to show that I've done this calculation, always show your work, like on the HSAT test. You had to show all your work for those 3 math problems that you're supposed to show all your work for, the constructed answer problems. So we're going to cancel that out and put in this number, 2.66 times 10 cubed millimeters of mercury. Okay? And we're ready to do the math now. Well, actually, now we can see we can cancel out millimeters of mercury. So we got 10576.16 Kelvin equals T2. Still need 3 significant digits. 1, 2, 3, underline everything else, and round off. Decimal place gets moved 1, 2, 3, 4 places. So 1.07 makes the 5 round up to a 6 times 10. 1, 2, 3, 4 to the 4th place Kelvin equals temperature 2. So practice problem number 4. Convert 77.0 liters at 18.0 torr to its new volume at standard pressure. So we're going to make a list of what we have. We've got 77.0 liters, and you know that measures volume. We've got 18 torr, 18.0 torr. I hope by now you guys know that measures pressure. We've got a new volume we're looking for, so that must be this volume 2, making this volume 1, and this pressure 1 at standard pressure. And what is standard pressure? We know that standard pressure is 1 atmosphere. You don't have to write it down this way. I'm just going to remind you guys of this. And on your test references, it shows you that it's 760 torr. 1 atmosphere equals 760 torr. So you don't have to even write down 1 atmosphere. You could just simply say it's 760 torr. Okay? Now you need to know that 760 torr, that 0 is significant. Even though it's not listed over here like that, that 0 is significant because there's 3 significant digits here. If we did the math, you'd have 3 significant digits here. All right, so we got P1 V1 equals P2 V2. What equation is that? That's Boyle's law. That's what we did the lab with. Okay, now on your test references in this particular class, you don't have that equation. You just have P1 V1 over T1 equals P2 V2 over T2. But the temperature is not changing here, so you can actually just drop the temperature off the equation and you got P1 V1 times P2 V2. Okay? Let's plug in what we've got. We've got a P1 of 18.0 torr. We've got a V1 of 77.0 liters, and that equals P2 of 760 torr times V2 we don't know, so we just leave that symbol like that. Same process we've been using all along. Isolate the unknown. This is the unknown right here, V2. Mathematically, we can isolate it by getting rid of the 760 torr by dividing by 760 torr, and that's an allowed mathematical operation as long as we do it to both sides. We can now cancel all of this and all of that. We can cancel torr on this side and plug it in. All right, so 1.82368421053 units we have left are liters, and that equals V2. Liters is a unit of measurement for volume, so we know we've set it up right, or more than likely we've set it right. All these numbers have 3 significant digits, 1, 2, 3 significant digits, and underline everything else. Throw an arrow to show we're going to round it off. Maybe we can get the door over there for me. And we get 1.82 liters equals V2. So I'm just going to show you the solution to this problem. A gas syringe contains 42.3 milliliters of a gas. So I'll list 42.3 milliliters of a gas as the volume at 98.15 degrees C. Here's 98.15 degrees C, but we need to change that into Kelvin. You can't leave it in degrees C, so I've taken that 98.15 degrees C, added 273.15, I get 371.30 Kelvin, and that's what I have right there. Determine the volume, so I've got a volume with question mark here to know that's what I'm trying to find. The volume the gas will occupy if the temperature is decreased, so I'm decreasing the temperature, second temperature, to negative 18.50 degrees C, which I had to convert to Kelvin And here's the math for that. 273.15 minus 18.50 gives you 254.65 Kelvin. That's what I have here. So I have volume 1, temperature 1, volume 2, temperature 2. That's Boyle's law. You can look that up on the test references for this class. It's sort of in this equation right here. This is the combined gas law, but pressure is not changing, so you can just drop off pressure 1 and pressure 2 and leave yourself with volume 1 over temperature 1 equals volume 2 over temperature 2, and that's what I wrote here. Plug in the values. Isolate this unknown here, this volume 2, by multiplying what's on the bottom here by the inverse in a fraction. Do the same thing to this side, cancel units. You get this long number in milliliters, and that's the volume. Round it off, show that with an arrow. Round it off to 3 digits because this number has 3 digits. And your final answer is 29.0 milliliters. Alright, so for this problem then, 73.0 milliliters of nitrogen is STP. So I've written down volume equals 73.0 milliliters. STP is standard temperature and pressure. Standard temperature is 0.00 degrees C, but you can't use temperature in degrees C when you're doing gas law problems. You've got to convert it into Kelvin, and 0.00 degrees C is equal to 273.15 K, and that's what I've listed right here. Pressure, standard pressure is 1 atmosphere. We can use that to make it easy. That's an easy value to use for standard pressure. And we're going to heat it to 80 degrees C. Going to change that to Kelvin. 80 degrees C, add to 273.15, you get 353.15 K. There's an empty slot here above the 5. Going to have to underline that to show it's an insignificant digit, show an arrow to where we're rounding off, and we get 353.2 K. That's what I put here. That's what I'll put in the problem. And it says the volume will increase to 4.53 liters. I've got that here. And we're trying to find what the pressure is. So I put pressure with a question mark. So given these unknowns, or these knowns and unknowns, knowns of volume, temperature, pressure, temperature, volume, and the unknown of pressure too, I can see this equation here, the combined gas law, which is on the test references for this class, right here. This is the one I want to use. So I want to plug in all the numbers, and I get this much of it right here. And then I'm going to try to get P2 by itself by multiplying by this, putting on the top of a fraction there, dividing by this, putting on the bottom of a fraction there. Do the same thing to this side. And when I do that, I will see that I've got milliliters here, but liters here. So you can't cancel milliliters with liters. You've got to convert liters into milliliters. That's what I did up here. I wrote down the equality statement. That's required. 1,000 milliliters equals 1 liter. I use that to build this conversion unit. 4.53 liters on the top of a fraction over 1. Using this conversion, 1,000 milliliters over liters, cancel liters. I get 4,530 milliliters. I need 3 significant digits because this number has 3. Round it off using scientific notation. I get 4.53 times 10 to the third milliliters. Now it's perfectly okay if you change this into liters instead. You can do that too. But I changed it. I changed 4.53 liters into milliliters. Then I'm going to multiply this. Well, first of all, I need to cancel the units. Make sure I've got all the units canceled. Make sure I'm leaving myself with a unit of measurement that's going to measure the variable I'm looking for, the unknown. Atmosphere is a measurement of pressure. So we know we probably set it up right. So then we'll multiply this times this times this. Hit enter in the calculator. Divide by this. Hit enter in the calculator. Divide by this. Hit enter in the calculator. And if you're talking your calculator's language, you should get an answer that looks like something like this, although your calculator may have a few less digits. That's fine. Round it off to 3 digits because this number has 3 digits, this one has 3 digits, and this number has 3 significant digits. So the leading zeros here are not significant. The first significant digit is the 2. Underline the insignificant digit, use an arrow to show it rounding off, and you get this answer. 0.0208 atmospheres is pressure 2. Alright, so this is problem number 2 on the homework. 1.09 grams of H2. You were asking about conversions to moles. Here it is. We've got a mass of 1.09 grams of H2. It's contained in a 2-liter container, so I've got a volume, 2.00 liters. Got a temperature of 20.0 degrees C. We want to know the pressure. We want the pressure specifically in millimeters of mercury. Okay? So I've got volume, temperature, pressure, and I don't really have an equation that directly gets there, but if I use PV equals nRT, if I find N, I've always got R. Okay, R is just given to you on the test references. I can find N because we've been doing that for a month, because we had to convert mass to moles. Okay, really simple conversion. To get N for hydrogen, I'm just going to take hydrogen, find the atomic mass of hydrogen on the periodic table. 1.008. What? And I've got 2 of these in a formula for H2. So times 2, 2.016. I don't have to add anything to this, so this is grams of H2 equals 1 mole of H2. Okay? So then I'm going to take this 1.09 grams of H2, put it over 1, use this equality statement to convert 2.016 grams of H2, 1 mole of H2. Cancel out grams and H2. Zero 0.54067 460 3175. I've got 3 significant digits here, so I'm going to find 3, 1, 2, 3 significant digits and underline everything else. This is moles of H2. Round that off. 0.54. This 6 makes a 0 round up to a 1. 541 moles of H2. So here we're going to say that's 0.541 moles of H2. Okay? So I've got pressure. I'm trying to find pressure. I've got volume. I've got moles. All I can look up, and T is 20 degrees C. Bells and whistles. Got to change that into Kelvin. 20.0 degrees C plus 273.15 to 93.15. Empty slot right there. That makes that 5 right here insignificant. That is Kelvin. 293.2 Kelvin. So this is 293.2 Kelvin. Almost there. Got to find which R to use. We want our measurement of pressure to be in millimeters of mercury, so we want to find the R value that has millimeters of mercury. And this is where that thing I told you yesterday comes into play. We said that torr, in this version right here of R, torr is the same as millimeters of mercury. It tells you right here that 760 millimeters of mercury is the same thing as 760 torr. So all I have to do is plug in millimeters of mercury for torr. It's exactly the same unit of measurement. So our version of R we're going to use is this one right here, 62.4 liters times, instead of torr, we're going to use millimeters of mercury. This says mole negative 1 exponent, which means moles goes on the bottom of the fraction. Kelvin negative 1 exponent means that Kelvin goes in the bottom. Okay? I want to try to find pressure, and I like to, and you don't have to, isolate pressure first. Does that make sense? So what I'm going to do is rewrite this, where I'm going to say, so I'm going to isolate or rearrange the equation so pressure is all by itself, and the equation is going to look like this, where pressure equals moles times the gas constant R times the Kelvin temperature T times 1 over the volume. And now we're going to set up the problem. Pressure is here, and I'm plugging in all the values that I have. Moles is 0.541 moles. R is 62.4 liters times millimeters of mercury divided by moles divided by Kelvin temperature. Then times the temperature, well, the temperature is 293.2 K, and then 1 over the volume, 2 liters. Cancel out everything we can cancel, and you see that you've got only the units of millimeters of mercury left, and that is a measurement of pressure, so we probably set everything up right. Pressure then is calculated to equal this number in millimeters of mercury. We only need 3 significant digits, so we've got to round off everything up to this 8 right here, and including that 8. So we've got to write our answer in scientific notation, move the decimal place 3 places, and we get 4.95 times 10 cubed millimeters of mercury. Pressure of a gas is reduced from 1200.0 millimeters of mercury. So we're going to write that down. 1200.0 millimeters of mercury to 850 millimeters of mercury. So we've got a pressure 1 and a pressure 2. The volume of the container is increased by moving a piston from, so this is what we're starting with, that goes along with this number. So that's a volume 1 of 85.0 milliliters to 350.0 milliliters, so that's volume 2. Again, you have to be very careful to read the problem and make sure you're putting the right numbers together, associating them together. What will the final temperature be? So we're starting with a pressure here and a volume here with a temperature that starts out at 90 degrees. So temperature 1 is 90.0 degrees C, which we have to convert to Kelvin. We're going to find the final temperature, T2, we don't know. All right, let's find our Kelvin temperature, 90.0 degrees C. I'm going to add 273.15 to that. There's an empty slot above the 5. $363.15 K. This 5 is insignificant. We round it off. And there's the temperature we want to use. All right. Pressure 1, volume 1, temperature 1. Pressure 1, volume 1, temperature 2. Combined gas law. Very good. So that's on your test references. Right here, over above my thumb. Okay. P1, V1 over T1. P2, V2 over T2. Plug in the numbers we've got. Now, I don't care whether you flip it now or flip it later. Doesn't matter. You're going to have to get T2 on the top of the fraction. You can plug stuff in, and when you see that T2 is by itself on the bottom, flip it then. Or if you're lucky enough to notice it here, you can flip it now. Okay? Now I think every time I do now, I flipped after I did it, right? So I'm going to go ahead and flip it now so I can see that I need to do this. Because I'm trying to find that number. So I'm going to write T1 over P1 V1 equals T2 over P2 V2. Now we can plug everything in. 363.2 K is T1. P1, 1200 millimeters of mercury. V1, 85.0 milliliters. Over on this side, we're trying to find T2. We don't know it yet. We'll leave that in there like that. Over pressure 2 is 850.0 millimeters of mercury. And V2 is 350.0 milliliters. Should have moved this over a little bit. I got to multiply by these two things to get T2 by itself. So I want to multiply by 1 over 850.0. Oh, I'm sorry. 850.0 millimeters of mercury goes on the top. I'm going to put it over 1. So I've got to multiply by the inverse of just this part here on the bottom. I want 850.0 millimeters of mercury times 350.0 millimeters on the top over 1, which if I've got this on the top times this on the bottom, I can cancel those. Got to do the same thing to this side. 850 millimeters of mercury times 350.0 milliliters volume over 1. So I did the same thing to both sides. I can now cancel 850 millimeters of mercury and 350 milliliters, leaving T2 by itself. That's the isolation step. I want to cancel millimeters of mercury here, milliliters here. Do the math. .0. I'm sorry, that's 850, isn't it? 850.0. Gosh, hit the wrong button again. Times 350. Times 363.2. Hit enter. Divide by 1200.0. Enter. Divide by this 85. I didn't divide? Oh, you're right. I didn't, did I? Try it again. We can take that number and divide by 1200. Enter. Divide by 85.0. 1059.33 continuing 3 Kelvin equals temperature 2. I need to round it off to 3 digits. This has the least digits here. So I have to move my decimal place 1, 2, 3 places and write the answer in scientific notation. So that's 1.06 times 10 cubed Kelvin equals temperature 2.